Now, one reason why this is interesting, if I let n equal 1, I would get that my area was between, let's see, that would be 3 minus 2 over 1, which would be, I'm sorry, which would be 1, and 3n plus 2 over n would be 5. If I let n equal 2, I would get that it had to be between 2 and 4. So you can see that that does bring it in a little bit closer. If I let it be 5, I get even closer. If I let it be 10, I would get between 2.8 and 3.2. And if I let it be 100, I would get that my area had to be between 2.98 and 3.02. Now these are all accurate upper and lower bounds, but obviously some of them are better than others. And you notice as your n increases, your bounds tighten, and you can see hopefully what this is heading towards. It looks like our area is probably actually 3 units for this problem. So we actually find that the limits of the lower and upper sums are exactly the same as n approaches infinity. So if we let f be continuous and non-negative on the interval from a to b, the limits as n approaches infinity of both the lower and upper sums exist and are equal to each other. So if you take the limit as n approaches infinity of the lower sum and the limit as n approaches infinity of the upper sum, you get the same exact value if it exists. So this actually defines the area of a region in a plane, and it's a way to find it exactly. If we let f, or a way to approximate it very, 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 very closely without any real problems. If we let f be continuous and non-negative on an interval from a to b, now this is important, it does have to be non-negative, so if you have your function dip below the x-axis on the interval you're talking about, you can't use this process. But the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is the limit as n approaches infinity of the sum from 1 to n of f of c sub I times delta x, where c sub I is some point between x of I minus 1 and x of I for each interval, and delta x is b minus a over n. So basically this is telling us we can choose our c sub I. It doesn't matter whether it's the highest, the lowest, or just some point in the interval, as long as we pick a point in the ith subinterval. And we can take this limit and actually get the area. So for this problem, it says find the area by the limit definition. This is the limit definition for area, bounded by the graph of f of x equals x squared, the x-axis, x equals 0, and x equals 2. So I'm going to sketch a graph of this. So this is an approximation of what my graph looks like. Notice that a is going to be equal to 0 and b is going to be equal to 2. So that means that delta x will be 2 minus 0 over n, or 2 over n. I get to choose my c sub I, so I'm going to choose the easiest c sub I to find and evaluate. I'm going to choose the right endpoints. Because remember from earlier we talked about how the right endpoints were a plus I delta x. So in this case that's going to be 0 plus I times 2 over n, which is 2I over n. And that's going to be really easy to work with. So I'm going to use the formula that I know. The area is the limit as n approaches infinity of the sum from 1 to n of f of c sub I times delta x. So that's going to be the limit as n approaches infinity of the sum from 1 to n of f of 2I over n times 2 over n, which in this case is the limit as n approaches infinity. F of x was x squared, so this is going to be the sum from 1 to n of 2I over n squared times 2 over n, or the limit as n approaches infinity of the sum from 1 to n. 2 squared times 2 is going to be 8. That's going to be over n cubed times I squared. So I'm going to bring the 8 over n cubed out of the sum, not of the limit. Notice that n is a constant with respect to the sum, but it is a variable with respect to this limit. So you can only bring it out of the sum, not of the limit. So when I apply my limit, or my sum formula, this sum of I squared is going to be n times n plus 1 times 2n plus 1 over 6. So cleaning this up a little bit, we can cancel one of the n's. We can cancel a 2 out of this, so this will be 3 and 4. So I would get the limit as n approaches infinity of 4 times n plus 1 times 2n plus 1 all over 3n squared. And if you multiply out the top, you would get the limit of 8n squared plus 12n plus 4 all over 3n squared. And since these have the same degree, this is going to be 8/3. So the area here is 8/3 units squared. Now looking back at that problem we were looking at in the last video, y equals negative 4x plus 5. If we went through this process, again, we would have delta x is 1 minus 0 over n, or 1 over n. We're going to choose c sub I to be the right endpoints, which are a plus I delta x. So this will be 0 plus I over n, or just I over n. And the area is going to be the limit as n approaches infinity of the sum from 1 to n of f of c sub I times delta x. So that'll be the limit as n approaches infinity of the sum from 1 to n of f of I over n times 1 over n. And we've actually already found this limit in the last video, so I'm not going to go through the algebra of that again. Or we've already found this sum, we haven't found the limit. From the previous video, we know that this sum is equal to 3n minus 2 over n. So again, since we have the same degree, this is going to be 3 over 1, or 3 units squared. So that would be the area of that shape.